Thank you for having me. I want to talk about a recent work of mine about Frechet means, actually. Um, Stefan has seen this, but there are some new things. Let's see. Okay, so what I want to talk about is, we start with this application. So for example, we want to do dimension reduction for manifold value data. And here's another application I can think of. So we want to do clustering for data on a metric space and how to do it. And the upshot is we can frame this task, dimension reduction for data on spheres, as a generalized Frechet mean framework. And we can also frame a clustering as a generalized Frechet mean. And with a little twist. So in the end, what I want to do is I want to show what are the conditions required to show that these methods applied to the data is consistent for a population counterpart. Okay, so this is the question that I could not answer entirely. But is there a unified framework for many statistical tasks on non-Euclidean spaces that can be used to guarantee consistency of the estimators? So I have only partial answers, and many of these were answered so far in time, actually. So one thing that I want to mention is that the generalized Frechet mean framework, if we extend the domain to be random, then many tasks can be framed as this framework. And I want to show there is a list of some conditions essential for guaranteeing strong consistency of the sample generalized Frechet mean to its population counterpart. Okay, and I want to show 2 or 3 examples of how this may be applied. So PCA for directional data and also for compositional data, and also k-medoids clustering for data on a metric space. If I have time, I want to discuss an extension of a weak law of large numbers to the usual Frechet means, but let's see if I have time for this. So we know what the Frechet means. So to me, Frechet mean is to take average of these 2 points. So if you want to take average of these 2, it's not 180 degrees. It should be 0 degrees. For this context, Frechet mean comes in very handy. So it's suggested in this slide. So if we take the argument minimum of the data space from the data points of the square distances to it, and then the Frechet mean of these 4 points is right in the center of the data. But if we take the naive mean, then it's on the other side. Okay. All right. So let me skip some slides actually. Okay, so Frechet mean is an extension of the sample mean. So if we think of the real line, then the Frechet mean of these 5 points is the minimizer of the sum of squared distances to each data point, and it's nicely convex, of course. And so this is the Frechet mean. We can think of something else. For example, instead of minimizing the sum of squared distances, we can think of minimizing sum of distances, for example, if p equals 1, or for any p mean. So we can think of the LP center of mass, or we can think of any form of loss function. So if we want some robust property, we can, instead of distance squared, we can use like Huber loss, and then it becomes a very robust estimator of the location parameter. All right, so Frechet means have been very useful. So we apply this to distributions and shapes, and for any objects that live in a metric space, we can apply the Frechet means. So one generalization of Frechet mean is to replace the squared distances to any loss function. Another generalization is to distinguish the data space and the parameter space. So the usual Frechet mean is for the case where the data space or the data x and the parameter mu are in the same space. So we want to estimate the location. So that is, so data and the location parameter lives in the same space. But let's consider fitting a geodesic, which is like straight curve to data on a sphere. So for example, if these are the data we want to fit a geodesic, in this case, this is just a great circle, in a way that the distance from data point to the geodesic and squared distances, some of those are is minimized. So in this case, the geodesic, the parameter mu is the geodesic. So data is on the sphere, but parameter mu is not exactly on the sphere. So a geodesic lives in the set of geodesics on the sphere. So these two spaces are not exactly the same. So Stefan has the idea. So when we have the random variables on a data space T, so x1 to xn, and then parameter lives in a metric space. So I'm going to call it parameter space. And there is a cost function to measure the discrepancy between the data point and the parameter point. So this cost function C quantifies the cost associated with using a descriptor or parameter M to describe a data point T in the data space. So we can think of two versions of generalized Frechet mean. So a key characteristic of the distribution P is defined as the parameter minimizing the expected cost. So this is the population parameter defined in this way. And to estimate this population parameter, we can think of minimizing the sum of cost functions. So this is going to be a natural estimator. This is the empirical GFM or the sample GFM. Okay, so in this case, it's the same setting. So if we want to fit a geodesic, so suppose these data points are sampled from a common distribution P, then we're fitting the least squared geodesics to the data. So cost of representing the data by a geodesic is defined by the minimum squared distance to the geodesic. And then this fits nicely to this generalized Frechet mean framework. So with some conditions, the empirical mean geodesic converges to the population geodesic as sample size increases. Okay, so here's another example. So principal geodesic analysis is very close to fitting a geodesic, but it's actually a sequential process. So I guess many people are familiar with PGA, but in short, so PGA identifies so this is a sequential dimension reduction problem. So given the same data, so we want to mimic what principal component analysis does for Euclidean data. So the first course is to find the average of the data. In this case, we replace the average with the Frechet mean, the usual Frechet mean. So that is the Frechet mean. And in order to find the first direction, so what we do is starting from the Frechet mean, this is right in the middle, we think of all kinds of geodesics that go through this Frechet mean. And the best fitting geodesic passing through this Frechet mean is the first geodesic, first principal geodesic. And once we have the first principal geodesic, in this case, is the figure is only two-dimensional, so two-dimensional sphere. So the second geodesic comes naturally. But if you think, if you have S3 or SP, is a higher dimensional sphere, then there's still a possibility of choosing the second principal geodesics that go through the average or the Frechet mean, and that is also orthogonal to the first principal geodesic. So this is the principal geodesic analysis. So if we want to frame this as the GFM, so in this case, we have data on S2. So data space is S2 with the natural metric, the angular distance as the metric. Parameter space is the set of all geodesics. So right now I'm thinking of fitting the first principal component, first principal geodesics to this data. the cost of representing the data by a geodesic gamma is given by squared distance from a data point x to geodesic gamma. So the previous framework of GFM almost works, except that the domains are different. So what do I mean by that? So we require the geodesic to pass through the Frechet mean. Okay, so I'm writing so gamma S2 means all geodesics on the sphere. Gamma S2 mu is the all geodesics on the sphere that goes through this particular point mu. So empirical first principle geodesic is a minimizer of this cost function, where gamma is chosen among all geodesics that goes through the sample Frechet mean, whereas the population version is the minimizer of the oops, I still haven't fixed this. So this should be expected value. I'm sorry, it's the population version. So minimizer of the expected cost of x1, because they all have the same distribution, to a geodesic, where geodesic is on S2 and it has through the population Frechet mean mu naught. Okay, so where the sample Frechet mean and population Frechet mean are, these are just typically different, of course. So here's an illustration of this, but let me skip this. So to frame this, we have to think of the random minimizing domain. So in empirical case, the domain depends on the sample Frechet mean, which is also random. But in the population case, the domain depends on a fixed parameter, the population Frechet mean. So this example motivates an additional generalization of generalized Frechet mean, accounting for potentially different minimizing domains for population and empirical versions. Okay, so this is the setting I have. So, so I'm trying to be as general as possible. So data space is any topological space. And we think of a random variable. We're going to think of IID sequence from the distribution. And parameter space is a metric space, and we have any cost function. Okay, so with that, population GFM is defined as the minimizer of the Frechet function, with the expected risk function, or the expected loss function, expected cost function, and is minimizer among some domain M naught. And empirical GFM is the minimizer of the empirical risk function, where the minimizer is found among in Mn, which possibly depend on the data. It may not depend on the data, but it possibly depend on the data. Okay, so Mn is not the same as M0, so that's why this is a little bit different. Yes.
You assume that the measure is unique in this case? Yeah.
The measure is unique. Am I assuming the Frechet mean is unique? Is that the question?
Equal.
The set. The question is A naught.
Yeah. Yes. Thank you. So E naught, En. This is a set. Yes.
Sorry, I'm confused that M naught, Mn are different. You probably have an example.
Yes. M naught, Mn.
Yeah. Well, did you give an example?
Yes. Possibly different. So let me go back. So here's the example. So this is Mn. So this is a set of geodesics passing through mu hat, the Frechet mean.
Oh, because so the restriction is it's not unique. Okay, good.
Yes.
Okay.
And this is M0. We have to change this to expected value. Okay. So this is the general setup. And there are many generalization of the usual Frechet mean to more generalized Frechet mean. So this is some list. I don't have everything. Well, we're thinking of the case where the data space may not be exactly same as the parameter space. We're thinking of a general cost function as much as possible. And the minimizing domain for the population M0 is possibly different from the minimizing domain for empirical. And both of these should lie in some bigger space, of course. That's M. Okay, so this is the main theorem, actually. So the question is, under what conditions can we guarantee the convergence of the Frechet mean set E hat N to population Frechet mean set E0? Okay, so the conditions, there are only three conditions. So one, we should have the sample domain Mn should converge it to M0 in some sense, and the requirement is that Mn converges to M0 almost surely in the Krotowski sense. That means we require Krotowski sense because there are cases where Mn is a subspace and M0 is a subspace. And when we think about the convergence of subspace to another subspace, if we think of that as convergence of set to set, then asking like Hausdorff distance becoming 0 is too much. So this is a little bit relaxed. And then that.
Inner and outer.
So right now so M0 is just one fixed
convergence.
Set. Convergence.
Inner and outer Krotowski convergence, and one corresponds to the Z-zone, the other to the Bhattacharya, but maybe that there's the Hausdorff in the middle. I think this in one of the papers by.
Yes. Well, yes. This is a little bit different from this. So what I mean by Krotowski convergence. So this is. So this set converges to M0, so Mn converges to M0. So Krotowski sense convergence means if you pick a accumulation point of the sequence of Mn, so pick one from M1, pick another one from M2, etc. If that sequence is as an accumulation point, that accumulation point should be in M0. That's one requirement. And another requirement is if you pick one element in M0, there must be a sequence from Mn converges to M0. So this is, yes, it's a little bit different. And there's a second and third condition. The second condition is basically we're asking all the nice things. So this cost function is continuous, and this cost function is also integrable, basically. So we're asking all the nice things. And then we can say that an estimator Mn lives in the sample Frechet mean set converges to some element of the population Frechet mean. So to partially answer Stefan's question, this is one-sided Hausdorff convergence. So not everything in E0 can be covered by a sequence here, but if you pick any sequence here, it will converge to E0. Okay. Let me skip this. It's a technical. So, so let's go back to principal geodesic analysis. So PGA sequentially identifies the best fitting principal geodesics, and we can think of this. So thinking of geodesics is actually does not fit to the generalized Frechet mean framework. So what we do is this at the case stage. So we have a mu lambda 1 gamma 1 hat to gamma k hat. These are k-dimensional geodesics, and these give the k-dimensional geodesic submanifolds of the sphere, and is a subset or the submanifold of the sphere. So in fitting stage, we start with the Frechet mean and find one geodesic passing through the Frechet mean that best fits the data. And if we extend the geodesic, this gives the S1. And in the second stage, you fit another geodesic. And the first geodesic and second geodesic gives the two-dimensional submanifold. That's S2. So we can think of instead fitting each gamma 1 and gamma 2. We can think of fitting subspheres with increasing dimension. Okay, so what the estimate of PGA is this: for each K, we want to find an S. What is an S? This is a subspace of dimension K, or subsphere of dimension K that contains Sk-1, which is K-1 dimensional subsphere. So suppose at the case stage, we already have K-1 dimensional subsphere. So I want just add another dimension. So this Sk should contain Sk-1. In the empirical case, we are minimizing some obscure distances, but in this case, our search space contains the empirical version of K-1 dimensional subsphere. So the only difference is that in the population, we have the population search domain, and in the empirical case, we have random search domain. And the M0 and Mn, these are contained in a bigger space, M, which is the space of all K-dimensional subspheres. Okay, so the PGA can be shown to be consistent? Yes.
You're dealing with more complicated manifolds. There be some issue in computation. Sure.
Just speak up.
Oh, so if you were dealing with a more complicated manifold, could there be issues in computing the Hausdorff metric to run this argument?
So in this case, a good question. So in this case, the subspheres, these subspheres are compact, so we can have a Hausdorff metric. There's no problem. But if we apply this to the usual PCA in Euclidean spaces, then instead of subspheres, we are looking at subspaces, affine subspaces, and and if you have a subspace and another subspace, and if the angle tends to 0, then in the Hausdorff sense, they don't converge.
Yeah.
So in that case, we have to use something else. But in this case, we don't have to use Hausdorff metric in this case, but it's
So
yeah.
so usually in case when you have these parameter spaces, often they're manifolds, stratified spaces themselves, so they have a distance themselves. So the space of G26, of course, is a manifold itself.
Yeah.
So you can actually use the distances of G26 or of subspheres or so. So all these are corresponding.
Well, this makes sense. I was just saying sort of like if you had like a less nice manifold and you were trying to compute this Hausdorff metric, could there be, I guess, issue like would the computation become cumbersome for computing the
Could be.
samples?
It could be. It could be. So so here I'm going to make sure that Mn converges to M0. And in some sense, in this case, checking that with Hausdorff metric is easy enough. In some other cases, it could be very technically difficult. Yeah. Thanks for the question. So how I do is I use the induction. So we start with the 0 dimensions. And we know in this case, with the nice assumptions, Frechet mean converges, the sample Frechet mean converges to the population Frechet mean. And that gives that Mn at the when we are fitting the first geodesic, Mn with the sample Frechet mean converges to M0 with the population Frechet mean. So other conditions of the theorem are easily verified because the space is so nice. And then with that, we can show that the first fitted S1 hat converges to S1 And that gives another, in the second stage, we have different domains, and that also converses. So it works inductively because we're doing sequential dimension reduction. Right, so there are some other applications, but I think most useful is to apply this to sequential dimension reduction, especially when we reduce the dimension in a forward sense. Then this framework works very nice. If we do the backward sense, then this framework actually doesn't work for that case. We need something more general and like Stefan's paper. Okay, so I want to spend how much time do I have? I have to finish by 3:30, I guess. 3:35. Yeah. Okay. Then I'll go through this example and skip the other one. So this works. So we have a PCA for zero inflated compositional data, and I'll explain that. And I will use the same framework to show what I'm fitting is actually consistent to something. Okay. So so this is about the compositional data, especially our application area was the microbiome count. So the microbiome count has a huge variability, so it's natural to normalize the compositional data. And sometimes the dimension or the number of taxa in the microbiome data is high, so dimension reduction is required. And the problem with the microbiome count is that many counts are zero. So it's a composition with many zeros. So that's why we want a different dimension reduction method for this kinds of data. So the microbiome data, it actually is just count data. So the raw data is yi star. Over there is just a count. And we close these counts. So divide each number by the total. So we make this xi is now a composition. Is all non-negative. It's a value between 0 and 1, and it x1 to xp sum to 1. Okay. So collection of these is a composition. So we have the compositional space, the CP, when we have p variables. Each xi is greater than or equal to 0, including 0 in this case, and sum of these values is 1. So this is just one data point, and we have many data points living in CP. Okay, so when P is 3, we can represent the compositional space nicely on a triangle. Ternary diagram to be anyway. So this is the case. Let's skip this. All right. So the common approach is to take the log. This is what people usually those people who do compositional data analysis, they do they take the log. So there is a log ratio PCA on old method, and it works pretty well for some data. It's not perfect for many data. The main problem is if there are some zeros in the data, we cannot take the log. So what we do is we replace the 0 with some small value. So simple replacement, we replace with some delta, basically. And if we have count level data, take delta as 0.5. But we also only have compositional level data, and delta is chosen to be the smallest non-zero value divided by 2. These are the usual choice. This is what I do when I analyze compositional data using logs. This is what I usually do. But it actually has some problem. So zero inflation may result in severe distortion. So this is simulated data. So we generate the data in this way. If we do log ratio PCA with, let me see, what is this? Okay, so if there were no 0, then log ratio PCA works pretty well. So this is one-dimensional approximation of the data. It goes through the middle of the data, so it works pretty well. But with 10% of zeros, then it starts to deviate from the main bulk of the data. So when there are more zeros, then log ratio PCA can behave not as expected. Okay. So our approach is to not to take the log transformation and take the triangle as the triangle. So this triangle is lives in a Euclidean space. We're going to use the Euclidean geometry. The one thing we can think of is we have data on this triangle, so we can just apply the classical principal component analysis. Then I have, like in this data example, I have a center in the middle and ignore the triangle, just apply the simple principal component analysis. And this is my first direction. But then I want to reconstruct or find one-dimensional reconstruction of the data. So I have to project this data point to this line, and it goes outside of this triangle. And this is not a composition anymore. So this may have value less than 0, greater than 1, or the sum of these values, well, they stay in 1, but typically they are less than 0 or greater than 1. So not a composition anymore. So one thing we can do is just to project the scores onto the compositional space. So this data point, when projected to the first principal component direction by the orthogonally projected is right here. So I can just pull it down to the triangle. So this is a simple method. I'm going to call it compositionally reconstructed PCA or CRPCA. This works okay for some data, but not greatly. So here is an example from a real data. So right now we are looking at the data itself. So I have 200-ish data point, and each data point is a composition. So you can see the first one has large composition of the red variable, some composition of the blue, etc. And we're looking at all the variables. And this is the original data, same data arranged differently. And here is the one-dimensional approximation of the data given by log ratio PCA. And this is one-dimensional approximation of the data given by the compositionally reconstructed usual PCA. And this is what I will present, but I have not yet discussed. This looks nice in one-dimensional approximation looks nice, but the deviation from the real data to the one-dimensional approximation looks really huge in this scale. CRPCA looks okay, but if you can notice, all of these points are reconstructed to be the same point, right? Because if all of these are outside of the triangle, so we have to pull everything down to 1 point. So that's not very nice. So we want something else that gives a nice approximation of the original data, and we want to prevent this to happen. So that's what I want to make. So how do we do? So we want to do. We're thinking of the reconstruction. So we want to find the direction and score at the same time. And if we reconstruct the data, so mu is the center, and V is the direction, and UI is the score for the ith observation. So this is the reconstruction of the data using our many principal components. And I want this to live inside the triangle compositional space. Okay. All right, so the mean vector is, so we're using Euclidean geometry, so mean is estimated by the sample mean in this case. All right, let me skip this. So to estimate this, we actually use sequentially. So what we do is we start with the mu, which is the sample mean, replace mu with the sample mean. And we, for the rank 1 case, we find the direction U1 and the score V1, and by making sure that once we reconstruct this is as close as possible to each data point X. At the same time, the reconstruction lives in the triangle. So we actually fit this using sequential or alternating minimization. But for the rank 2 case, now we are fitting, what is this? I'm sorry, I have spoken the other way. So we're fitting the direction V2, second direction, orthogonal to the first direction. And we are adjusting the scores so that the reconstruction is as close as possible to the data point and they live on the triangle. So that's what we do. Okay, so that's basically, this is for the k-dimensional case. Okay, so this can be computed. So we don't know if what we can compute is the minimizer of this, but we believe we can get, this is not a convex problem, so we don't know if the computation goes very correctly. But the question is, if we do this with huge sample size, does it converge to somewhere? So there is the question. Okay, so for this, we want to reformulate this problem. So the previous problem has the direction and score. So we're wiggling with both, and that's too complicated. So the idea we had is instead of working both scores and the direction, we can make this using the projection operator. So pi of z of x is projection of x to a subspace z. So we want to this CS. So this is our cost function. So we want to find a compositional subspace. And when xi is projected to this CS, which is the subspace, and the discrepancy is as small as possible. Okay, so the proposed problem can be written in this way. So the risk function is written this way, and we're the compositional subspace should contain, we're looking at the k-dimensional compositional subspace. It should contain k-1 dimensional compositional subspace. And the population version, I have the same cost function. The difference is now we're looking at the expected value. And the search space should contain the population k-1 dimensional subspace. Okay, so this fits very nicely to the generalized Frechet mean framework. So we will show the estimated compositional subspace converges to the population version, and each direction that we are actually computing also converges to the population direction with sign flip allowing. Okay, so this becomes a generalized Frechet mean. All right, so given time, let me skip all of this. It's the same story. I think I have discussed this, and let me skip this, and I want to discuss actually something new. All right, so I discussed a generalized Frechet mean framework. This extends the Frechet mean and also can be thought of as the M estimation framework. And especially I'm thinking of the potentially different and random minimizing domains. And there are some open problems. So I'm thinking of, can we apply this to weighted Frechet mean or conditional Frechet mean? And the result I have is only about the law of large numbers or convergence of the sample Frechet mean to population Frechet mean. So can we have a general theorem for central limit theorem type thing when the parameter space M is nice enough? And can we extend this result to a non-IID sequence for the random variables? So far, I'm assuming IID sequence following common distribution P, and I have strong assumptions on P as well. Can we relax this condition? And I have the moment condition, so this cost function when integrated it should be finite. Can we relax this condition? So I want to answer some questions regarding the last point, but I don't have answer for this general framework. I have partial answer for a very special case of the usual Frechet mean. So let's go back to the usual Frechet mean case. So the data space equals the parameter space. We're looking for the average, basically. The consistency. So for now, let's assume that the Frechet mean is actually unique. So the minimizer is mu n, which is the unique sample Frechet mean, and mu is the unique population Frechet mean. And convergence of mu n to mu is usually derived for IID sequence, and usually for the case where second moment exists. Of course, this can be extended to the case where only the first moment exists, but then we have to redefine what we mean by Frechet mean. Okay, so can we extend the consistency of the Frechet mean beyond IID sequence of random variables with finite second moment or finite first moment? So so we looked at the probability textbook, and there is this Kolmogorov-Feller-Wick law of large numbers. So with this tail condition, so this is about the real valued random variable x1 to xn IID sequence from a common distribution P. If the P satisfies this tail condition, then this thing holds. So if you look at this, the first one is just the average x bar minus n cancels, then is the expected value of x1 times this one function with x1, the magnitude of x1 is less than equal to n. And this difference converges to 0. So this result can be extended to independent but non-identically distributed sequence. There are extensions of this result to non-independent sequence as well. But we're looking at only the partial result. Okay, so we wanted to extend this to the manifold setting, but the Frechet mean can be non-unique, which make things very complicated. So we're looking at negatively curved space. So we're looking at symmetric spaces, and it's non-compact. So it should be Hadamard space. And in place of this truncation, we have to replace this truncation by something. So we're assuming symmetric distributions as P. Okay. So what I'm assuming is this. So the space is a non-compact symmetric space, which is Hadamard, and there's a unique Frechet mean, and it also comes with a unique geodesic symmetry for any point nu of M. So we can define symmetric distribution, including isotropic and elliptically symmetric distribution Px. So I'm going to think of the distribution I'm thinking of is this lives in a symmetric space, and the distribution itself is symmetric. And this is quite important because I don't know otherwise how I can define what is the center, because I'm not going to use I'm going to relax the second order condition, which means that Frechet mean may not be well defined. So we need a center.
Is it so clear that a non-compact symmetric space is Hadamard?
That's what I thought. Yeah.
So there's a theorem. So for example, the Beltrami trumpet is probably not symmetric.
I'm assuming, so I'm starting with the symmetric space and assuming non-compactness, and I think I have seen a result that, so we'll see the details later. Okay. So so non-compactness being the space being symmetric, and also we have unique geodesic, everything is used actually. Yes. Okay. Then with this case, if we have IID sequence xi, so this is my typo, xi IID sequence from Px, and if this tail condition is satisfied for some point, and this some mu0 can be replaced by mu, that makes a little difference. If this tail condition is satisfied, then mu n converges to mu in probability, not almost surely. Okay, so this is the first result. So for example, if the distribution satisfies this tail condition, so probability that x1 distance of the random variable from mu greater than some value t is proportional to this specific form, then the first moment is infinite, but this tail condition is satisfied. And in this case, the sample pressure mean, this always exists. This is a consistent estimator of the center of symmetry mu. So in this case, I couldn't say this mu is the pressure mean because pressure mean is not technically defined, but this is for sure center of symmetry. Okay, so the second result is this. So now we have a sequence xi, but they are independent, but they are not identically distributed. The requirement is that all of these has the same center of symmetry mu. Now with that, we have the tail condition. Instead of n times probability, in this case, I have sum of probabilities of the tail that tends to 0. And if you truncate the random variable at distance n, then this condition satisfies. With these two conditions, then we can show that the sample pressure mean mu n converges to population center of symmetry. Right, so here's another example. So this example, we're looking at the positive symmetric, positive definite spaces. So xi is an, and that comes with affine invariant metric. Okay, then we can just take the log. And if we take the log, it follows some normal distribution. And as you can see, in this case, mu, which is the, in this case, I'm looking at the identity. This is the center of symmetry. But pressure variance, if you compute pressure variance, is I to the power of alpha times a constant. And I is the sample index, and alpha is a value between 0 and 1. So this pressure variance increases. Okay, and they are not identically distributed as well. And then in this case, we can check those two conditions are satisfied as well. So the sample pressure mean mu n converges to mu in probability. Right, so that's all I wanted to say. So we talked about generalized pressure mean, and we also talked about relaxation of conditions required for consistency of the usual pressure mean. There are many open problems. So we have not talked about, so I'm assuming the sequence is independent, and there must be a way of allowing some dependence in the law of large numbers. And I have assumed symmetric distribution. This can be, so symmetric distribution with the same center of symmetry, but we can relax this a little bit further. Okay. So this work is done with my former PhD student, my current postdoc, Jae-sung, and my co-worker, Jung-min, and my former postdoc, Ki-Pung Kim. So thank you very much.